All right, welcome to the introduction to section 4.1. We're going to start talking about area between functions and the x-axis, and we're eventually going to find an efficient way to calculate these areas, but we're going to have to build up to that like we did with limits and derivatives. So the first question here is, what is the area between f of x equals x plus 1 and the x-axis on the interval from 0 to 3? So let's see, at 0 I can go up to the curve, so here's one bound of my region, and I can do that same thing here at 3. So it's this area, shaded in pink here, that we want to find. And we could do that a couple of ways, I guess. Maybe the easiest way would be to break this area into two shapes we're familiar with, one being a rectangle and one being a triangle. So I can call this area 1 and area 2. So area 1 is the area of a rectangle. It is 1 unit high, and it is from 0 to 3 units wide, so its area is 3 square units, whatever our units are. And area 2 would be the area of a triangle. Let's see, it's also 3 units wide, we can see that here. And tall, let's see, it goes from 1 up to 4, so it is also 3 units tall, and it's a right triangle, so its area is 1/2 3 times 3, or 9/2 units squared. So if we add area 1 and area 2, we could get the total area. It's 3 units squared plus 9/2 units squared, which is 15/2 square units. Okay, it works out nicely when that area can easily be defined by geometric shapes that we're familiar with. Not quite as nicely, though, when that function is something like x squared. Okay, so here we're going to estimate the area between x squared and the x-axis from 0 to 3. All right, we're going to do this 3 ways. We're going to create what's called a right-hand sum with 3 subintervals, a left-hand sum, and a midpoint sum. And I'll draw what I mean by those very specifically here in a second. But first of all, let's see how wide each interval should be. So in each case, we're going to have 3 subintervals. So we're going to let delta x be the width of each interval. So what is delta x going to be? Well, it's going to be the length on the x-axis divided by the number of intervals. By length on the x-axis, I mean, where are we looking? We're looking from 0 to 3, so the length of that full interval on the x-axis. So in this case, it's 3 minus 0 divided by 3, or 1. So delta x is width 1. So each of our intervals we're going to create are going to have width 1, and I'll show you what I mean by that. So we're looking from 0 to 3, so we're going to have an interval here, we're going to have the endpoint of an interval here, we're going to have the endpoint of an interval here. Okay, right-hand sum, what the right-hand sum means is use the right-hand endpoint of your interval. So from 0 to 1, this is the right-hand endpoint. 0 to 2, this is the right-hand endpoint. 0 to 3, this is the right-hand endpoint. Use those endpoints as the height of rectangles on that interval. Okay, so I use this endpoint as the height of a rectangle on the interval from 0 to 1, this one on the interval from 1 to 2, and this one on the interval from 2 to 3. And so our right-hand sum with 3 subintervals is going to be the area added up of those 3 rectangles. Well, let's see. They all have width 1. We know that. And what are their heights? Well, this first rectangle has height, the value of the function at 1. 1 squared is 1. This second rectangle has height, the value of the function at 2. So it has height 2. And this third rectangle has height, the value of the function at 3. So that's 3 squared, or 9. So how we would notate this is we would say that r sub 3 is equal to the sum of those rectangular areas. So the first one has area 1 times 1, plus the second one has area 1 times 4, plus the third one has area 1 times 9. We add those up, we get 1 plus 4 plus 9, or 14 square units. So the right-hand sum with 3 subintervals would give us 14 units squared. And we can see very quickly, that the right-hand sum would be an overestimate for this area that we are trying to estimate. Let me draw that in. So the area that we're trying to estimate is this area, which we can't find nicely with a geometric shape or figure like we did above. So we get an estimate of 14 square units. Okay, we can do something similar with the left-hand sums. So again, we have 3 subintervals, so that's 0 to 1, 1 to 2, 2 to 3. Now go to the left-hand side of each subinterval, so that's right here, already on the curve. That's right here, and that's right here, and use those as the heights of rectangles. Okay, there's a rectangle, there's a rectangle, and there's a rectangle. So now we have 3 rectangles. The area that we're looking at comes all the way over here. Right? So if we add those together, clearly we would have an underestimate for the area between the curve and the x-axis. This first rectangle, what does it look like? It has width 1 and height 0. The second rectangle, it has width 1, that's right here, and it has height right here, which is also 1, the output of the function at 1. And that third rectangle, well, they all have the same width, it's delta x, which we decided was 1. And the height here is the output of the function at 2, which is 4. So L3 gives us 4 plus 1, or 5 square units. Clearly an underestimate for the area between this function and the x-axis. Okay, we can find this estimate one other way, using what's called the midpoint sum. So the midpoint sum, well, instead of left, right, we're going to go to the middle of each interval. So we have an interval from 0 to 1, 1 to 2, and 2 to 3. We're going to go to the midpoint. We're going to go up to the curve, and we are going to use that as the height of our functions, of our rectangle. So in this case, that's at 1/2. It happens again here at 3/2. We use the output of the function at 3/2. It happens again here at 5/2. Okay, so the width of our rectangles didn't change because the width of our intervals hasn't changed. The thing that changed quite a bit is how we find the heights. So let's see, we're at 1/2, 1/2, 3/2, and 5/2. And the height of each of those rectangles, for example, if I draw the one in here at 5/2, is the output of the function at 5/2. This point right here on the curve is the point 5/2, comma, 5/2 squared. Right? It has y value, 5/2. So the midpoint sum here with 3. Well, again, each rectangle has width 1. The first rectangle has height 1/2 squared. That's the output of the function at 1/2. The second rectangle has width 1 and height output of the function at 3/2. And the third rectangle has width 1 and height output of the function at 5/2. So what do we get? 1/4 plus 9/4 plus 25/4. So we get 35 over 4, or 8 and 3/4 square units. That's a much better estimate. We can see our rectangles both over and underestimate depending on which side we look at. It's pretty close to the average of those first two estimates also. All right, you can imagine now that if we did more and more subintervals, the more subintervals we had, and if we went to 6 or 12 or 24, the narrower our rectangles would be and the better our estimate would be. So that's where we're heading in the long run. On the activity, you can try to calculate these sums with 6 subintervals and see that you get better estimates than with 3 subintervals. Okay, we want to generalize this work just a little bit. So we want to find the left-hand sum with n subintervals. Okay, so here's how we're going to do this. Delta x, again, is always the width of each subinterval. Okay, and it always looks like the width of the interval, the width of the full interval, divided by the number of subintervals. Okay, so in this case, we're still looking from 0 to 3. And in this case, delta x then is the width of that full interval, which is 3 minus 0, divided by the number of subintervals, which is 3 over n. Okay, so I'd like to, let's take out the x-axis here, this piece of it that we're looking at. We're looking from 0 to 3. And let's see if we can just mark on the x-axis the spots where we are interested in our subintervals. So we move 3 over n units away from 0, and that's the first endpoint. And then we move again another 3 over n. So each of these times I move, here's a delta x, here's a delta x. When I move again 3 over n plus another 3 over n, that's going to get me to 6 over n. And then I move again, and again, and again, and again, and eventually, I don't know what n is, right? N might be changing. So eventually I get down here close to 3, and then eventually I do get to 3. And each of these subintervals have the same width. It's delta x, which is 3 over n. That happens all the way across here. So I can label these points on the x-axis. I go from 3 over n to 6 over n, to 9 over n, to 12 over n, to 15 over n, to eventually I get to 3n over n when I've gone far enough. And the one right before this is going to be n minus 1 copies of 3 over n. I have 1 copy, 2 copies, 3 copies, 4 copies, 5 copies, n minus 1 copies, n copies of 3 over n. And so you could think of this as 3 over n times n minus 1. And this one you could think of as 3 over n times n. This is 1 copy. This is just 3 over n. This is 2 copies of 3 over n. This is 3 copies of 3 over n, etc. Okay, so now we want to have the left-hand sum. So now I'm going to come back up here and I'm going to put some of these in here on the x-axis so we can see what's happening. I'm going to blow up these intervals so that we can see. Here's 0. Let's say this is 3 over n. And then we decided we moved to 6 over n. And then 9 over n. 12 over n, etc. And eventually we got down here to n minus 1. Oops. Can't get rid of it. There we go. There we go. All right. We got down here to n minus 1 copies of 3 over n. And here we had got to n copies. Okay, so now we're using these left-hand endpoints to draw our rectangles because we're doing ln, so it looks like this. And then like this. And then we have a bunch of them in here. And our last one is going to go from this spot, which was 3 over n. Let's see if I can draw it in. Okay, so now what does this, can we generalize what's happening here in terms of these areas? Let's just focus in up here on a few of these rectangles. So on this rectangle right here in orange, what's the width? Well, the width is delta x, it's 3 over n. What's the height? Well, the height is this distance right here. This distance is the output of the function at 9 over n. So this height is 9 over n squared. Similarly over here, this height is 6 over n squared. Similarly here, this height would be 3 over n squared. So we take the endpoints of our intervals into our function, and that's going to give us the height of our rectangles. And so what does this give us? This gives us that ln. Well, the first rectangle had width 3 over n, and it actually had height 0. That was this rectangle up here, because we started with left-hand endpoints. Then we got to a rectangle that had width 3 over n and height 3 over n squared. That's this second rectangle right here. It has width 3 over n, and the height is the output of the function here at 3 over n. The next rectangle right here, width, always the same, 3 over n. Now this time the height is the output of the function at 6 over n. Then we get that next one that we saw, 3 over n times 9 over n squared. We see a pattern going on here. All the widths are 3 over n and all the heights are 3 over n squared, plus we keep adding 3 over n until we get down here to our last rectangle. Whoops, sorry about that. Our last rectangle right here. Here's another copy of delta x, which is 3 over n. And here is the point on the function that looks like n minus 1 copies of 3 over n, comma, n minus 1 copies of 3 over n squared. That's that point. And so here is the height of that rectangle. The width is 3 over n, and the height is n minus 1 copies of 3 over n squared. So there is Ln. We can simplify that a little bit. Each one of these terms looks like it has a 3 over n in it. So it looks like 3 over n times, we're going to have a 3 over n squared plus 6 over n squared plus 9 over n squared plus, plus 3 over n times n minus 1 quantity squared. Okay, we could simplify ln a little bit more if we wanted to, but the point is being able to write it down for now. So you'll have a chance to try to generalize Rn. It's a challenge as part of the activity, but definitely a challenge worth taking because this is how we're going to initially be able to calculate these areas. We can write down a right-hand sum, and we can ask ourselves what happens when n gets really, 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 really large. The larger n gets, the better our estimate should be. And so that's where we're headed in section 4.2. One more idea here is how does this work? What does this look like in context? So we have a particle in motion has the following velocity function in feet per second at given time. Estimate the distance traveled in 30 seconds. Okay, so here I've tried to graph this, and let's remember here, time is in seconds, and this is velocity on this axis in feet per second. And we want to estimate the distance traveled. Well, they're drawn in some rectangles for a reason, right? And let's see what happens if we find the area of one of these rectangles. So if I look at this first rectangle, it has width 5, as they all do. And what is its height? The height of this rectangle right here is just the output of the function at 5. I used a right-hand sum. The output of the function at 5 is 36. Okay, so this first rectangle, I'm going to call it R1. R1 has area 5, which its units are seconds, times 36, which its units are feet per second. And those units are definitely going to give me feet when I multiply. So that is 180 feet. So I get a distance when I find the area of that rectangle. And so that distance is the distance traveled from 0 to 5. And now I want to estimate the distance traveled in the first 30 seconds. So I could do this at 5-second intervals, finding I could do the right or the left-hand sum here. I have done the right-hand sum. So our estimate for distance traveled on the interval from 0 to 30 is, well, we already got the first rectangle. That's 180 plus they all have width 5. The second rectangle has height, the output of the function at 10, which is 40, you see in the chart, plus 5 times the output of the function here at 15, which is 44, plus 5 times the output of the function at 20, which is 52, plus 5 times the output of the function at 25, that's going to be this rectangle. The output of the function at 25 is 47. And finally we get, let's see, I can fit it in here, 5 times the output of the function at 30, which is this rectangle, and that is 41. So here's our estimate for the distance traveled. Let's see, can we do this? That's 180 plus 200, sorry about that, plus 220 plus 260 plus 235 plus 205. Okay, let's see. Can we add all of these things together? Let's see. I think we can do it. These three add to 600. These two add to 440. Add this one in with this one gives us 700. So it looks like 1,300 feet is our estimate. Okay, see if you can use that. I know that was a quick run through LM there. You'll see some examples in the textbook if you look at it. If they're not in 4.1, they might be in the beginning of 4.2. See if you can do that challenge on the activity to write down Rn, and then obviously I will post the solutions to that activity as well, so you can see how that falls out in those solutions also. And then once you do that, take a stab at the homework that is assigned in the text.